Professor Tabony uses the approach from self-organization to swarm intelligence in reacting systems, taking microtubules as an example. He will give a brief overview of the historical background to reactive self-organization, illustrating the underlying concepts with examples from his own work on in vitro microtubule preparations. Welcome, Professor Tabony.
Well, thank you very much. I'd very much like to thank the organisers for the great pleasure of being here today. And some months ago, Professor Sahni wrote to me and asked me to give a vision talk. Unfortunately, I don't have a vision. But this man, whose portrait you see here, the blind Puritan poet John Milton, certainly did. And here I've put up some extracts from his epic poem Paradise Lost, in which Milton considers the emergence of the world we know from a type of primeval soup, in which, as he says, without bound, without dimension, where length, breadth, height and time and place are lost. And so it's quite clear that John Milton considered the development of self-organization and position information as one of the fundamental aspects in the emergence and development of the world and life as we know it. Of course, in the intervening 350 years, not everybody has shared the vision and opinions of John Milton. And for example, the laws of thermodynamic equilibrium tell us that, on the contrary, that any existing order which may exist will be progressively lost over time. Now, biology, living systems, are characterized by pattern, order and form, and one of their characteristics as well is they're not at thermodynamic equilibrium. On the contrary, they're out of thermodynamic equilibrium due to the chemical and biochemical reactions which are continuously going on within living cells. However, as you know, if we carry out a chemical reaction in a test tube, in most cases the solution does not self-organize and no positional information is generated. However, very slowly and progressively, often against much opposition over the last 100 years, theoreticians and experimentalists have shown that this is not always the case, and that some particular types of chemical reactions which show strongly nonlinear properties due to the fact that they're sufficiently far from equilibrium, can spontaneously self-organize. Now, at a molecular level, this self-organization is a result of a combination of reaction diffusion, chemical energy is consumed, and progressively a stationary chemical pattern develops. Now, structures of this type are sometimes called Turing structures, after the name of the mathematician who was one of the first people to propose such a mechanism back in the 1950s. And they're also known as dissipative structures. And this term was employed by Prigogine and his co-workers in the 1970s because a flux or dissipation of chemical energy through the system is required to drive it sufficiently far from equilibrium so that self-organization can arise. Now, in addition to self-organization, it's also been predicted that systems of this type could also show bifurcation properties, in the sense that the presence of a weak external factor at a critical moment early in the process can determine the type of morphology that subsequently develops. And indeed, Prigogine and co-workers explicitly predicted that gravity and electric and magnetic fields can have this effect. Now, these chemical self-organizing systems of this type form a particular category of what are now called complex systems. And the complex system is comprised of a population of strongly coupled elements which are connected together in a non-linear way in such a manner that new so-called emergent phenomena develop. And these emergent phenomena are not the properties of the individual element as such, but they're the global properties of the population as a whole. And self-organization is a major emergent phenomenon. Now, in some types of complex system, an emergent phenomena as it develops can modify the global behavior of the population, and this can give rise to the development of a new higher order emergent property, and you can get in some cases you can get a sequence of developments of this type, which can even extend up to what some workers term as swarm intelligence. And very well-known examples of this are the collective behavior of social insects such as ants and bees, things like this. Now, and some workers, some scientists even believe that life itself is an emergent phenomenon. Now, in biology, one of the aspects lacking has been an example of a simple in vitro biophysical, biochemical system in a test tube which behaves this way. Now, it turns out that under appropriate conditions, the in vitro formation of microtubules, a major cellular component does show this type of behavior. These preparations self-organize by reactive processes. Self-organization can be triggered by weak external factors such as gravity and magnetic fields, and higher order emergent phenomena develop, which can even extend to such an extent that under appropriate conditions, a population of microtubules can spontaneously behave like a miniature machine. And this is what I'd like to show you today. So I'll break this talk up in the following way. First of all, I'll give you some examples of some very well-known self-organizing systems, and then I'll say a few words about microtubules, and then I'll go through the experimental behavior of this system. And I'll try to minimize the number of details I give you, so as to not take up too much time, not to make it too complicated, but I'll be very pleased to answer any questions you may have afterwards. Now, first of all, some self-organizing systems. This is here, we have a self-organized structure, and the energy causing this structure, it's a physical system, is heat. It's convection currents. What you see here is a Petri dish. It's a Petri dish about 8 centimeters across. It contains a thin layer of silicon oil, and it's being heated from below. And as you heat it from below, there's a decrease in density, and the warmer liquid at the bottom eventually destabilizes the liquid and starts to rise. And under appropriate conditions, these convective currents self-organize in the way that you see here. Now, of course, when you stop heating, convection stops and the structure disappears. And so this is a very well-known example of this dissipative structure. Now, this slide is an illustration of a simple type of bifurcation phenomena. What we have here, on the vertical axis, we have some sort of state variable of the system, and on this horizontal axis, we have the distance of the system from equilibrium. Equilibrium is here, and here, over here, we're far from equilibrium. And systems which are at equilibrium can be described by linear equations. Y is mx plus c, in which case there's only one solution, which is everywhere the same, and the system is homogeneous. Systems which are far from equilibrium are described by nonlinear equations. And for example, it may be a quadratic. And now for any given experimental conditions, there can be more than one solution. It can be two solutions. These solutions, in some cases, are real and can correspond to states of different morphology. Now, if we start here at equilibrium and we gradually move away from it, first of all, we just have a perturbation on the equilibrium state, which remains stable. But eventually, as we go further and further away, we get to a point where this, the linear solution becomes unstable, and the nonlinear solutions arise and become stable. Now, at this critical point round here, the system has to decide which pathway it takes. And as you can imagine, the presence of any small factor which favours one pathway over the other will determine the morphology of the state which subsequently develops. And of course, once the system has taken this pathway, you can remove the small perturbing field, and has no further effect. So it's the presence of a small field at this critical moment of instability which determines what happens subsequently. Now, here's another physical example, very well known. What you see here is two cylinders, one inside the other, and it contains a viscous liquid between the two, and we can turn one with respect to the other. And as initially the liquid is still, there's no structure to be seen, and as we turn it faster and faster and faster, gradually structures of this type develop. And what you're seeing here are periodic variations in the velocity of the liquid between the two tubes. And if we go faster than this, we can destabilize this structure at its turn, and then there's another series of more complicated bifurcations and structures, and we eventually end up with chaos. Now, this is an example of a chemical self-organizing system. This is what's called the Belousov-Zhabotinsky reaction. It's a rather complicated oxidation-reduction reaction. The details don't concern us here. What is the major feature is you mix the chemicals up in a test tube, which is about 10 millimeters diameter, and the solution is homogeneous. The reaction gets going, and progressively after about an hour, the sort of striped arrangement that you see here develops. And these stripes correspond, the colours correspond to periodic variations of the concentration of some of the reactants in the test tube. As the reaction proceeds and the chemicals are consumed, and the reaction slows down and everything's finished, then the normal processes of diffusion and convection destroy the structure. Now here, I've put around here I've put the photographs of some of the principal contributors to this field, and this gives me the opportunity to digress just for a few moments and go through some of the history of the development of these self-organizing chemical structures. Around 1910, a Polish person, Alfred Lotka, working in America, he developed theories of oscillating chemical reactions, but his work was so poorly received that he was discouraged. He went to work in the life insurance industry, where he made a fortune. About 10 years later, once again there were some reports from American workers experimentally showing the presence of oscillating chemical reactions, but their work was either ignored or dismissed out of hand as being due to bad experimental practices. And about 20 years later, there was some more theoretical work, one by an eminent Soviet physicist called Mogorov, and another by from the University of Chicago by Rajewski, who developed theories in predicting the partial separations of chemicals by reaction and diffusion. And once again, these articles don't seem to have had a great deal of impact. The situation started to change in the early 1950s. First of all, Belousov, who I showed earlier on, developed his oscillating chemical reaction. But when he tried to publish his work, it was refused by the referees on 3 occasions because they said it was impossible, it couldn't happen. And discouraged by this, Belousov retired from science. Not later, in the early 1960s, because Belousov's recipe was still known in the Soviet science community, it was taken up by Zhabotinsky and Zaykin. They modified it so that the reaction showed the self-organized stripes I showed you, and they also modified it so that you could actually see the differences in concentration by different colors. And this became available to Western scientists in 1967, 1968, just before the Russian tanks moved into Prague. Not long after this, 1952, Turing published, one of the inventors of the computer published his last article in which he developed a reaction diffusion theory for the development of self-organization by reaction diffusion. This article had much more impact. And then in the 1970s, the approach was further developed theoretically by Prigogine and his co-workers, essentially in terms of far-from equilibrium systems. But it wasn't until 1990 that the variation of this chemical reaction discovered initially by Bray in 1921, that experiments conducted by a group in Bordeaux was at last accepted as the first example of a Turing or Turing-like structure. So there's a long history difficulties and opposition to these concepts. Now, I'll now go back to where I was, another example of self-organisation. This is of a living system, and this is the self-organisation of ants. Well, as you know, ants self-organise to form these long columns with which we're all familiar. And then this occurs not because there's somebody's giving instructions to the ants, but because ants lay down trails of chemicals called pheromones, which attract or repulse other ants. And when an ant wandering around looking for food, when it finds someone, it goes back to the nest and lays down a trail of an attractive pheromone, and then another ant coming along, when it finds this trail, it follows it up, and it goes back to the nest, and it lays down its own trail of pheromone, and it reinforces it. And the progressive reinforcement of these trails leads to all the ants self-organising into these columns. Now, if you have several food sources around a nest, the ants will progressively accumulate onto the food source which is closest to the nest. And this occurs quite simply because the distance being shorter, the pheromone concentration accumulates more quickly. And if you have two food sources which are exactly equal distance one from the other, the ants will still eventually accumulate onto one food source rather than the other. And this comes about because any small factor or effect which favours the development of the pheromone chemical trail in one of the food sources will eventually lead to all the ants accumulating onto this. And this is an example of a simple bifurcation phenomenon in a living system. And as I'll try to show you, there are many analogies between the way ants self-organise and the way microtubules self-organise. Now this brings me to microtubules. As their name suggests, they have a tubular form. They're about 300 angstroms in diameter. They're several microns in length. And the walls of these tubes are made up of a protein called tubulin, which has a dimension of about 30 angstroms. Now, what is particular about microtubules is that they're not static objects, they're dynamic objects. They're continually growing and shrinking from their different ends. And this is associated with chemical reactions in which GTP, a nucleotide, is hydrolyzed to GDP. And one very important particularity of them is that their different ends have different polarities, and they grow and shrink at different rates according to them. So one end will be growing, and the other end will be shrinking. Tubulin is added onto one end, tubulin is liberated at the other, and GTP is hydrolyzed to GDP. And this type of behavior is strongly nonlinear. All it needs is a very small change in reactive conditions at either of these ends, and you can find that all of a sudden one end starts to shrink very quickly, and the microtubule almost disappears, or it can grow very quickly, or you can have an intermediate situation where the rates of addition and loss are almost equivalent, and then you see the microtubule more or less move across the solution. It doesn't move, but it's growing in one end and disassembling and disappearing in the other. Now, microtubules are quite important things in cells. They form a type of scaffolding within a cell, and they're responsible for determining cellular organization and the transport of subcellular particles from one part of the cell to another. Brain neuron cells contain a very large proportion of microtubules. They play a major role in cell division, and for example, during the cell cycle, the microtubules initially are relatively disorganized, and when the cells come to division, they disassemble and reassemble in these aligned arrays, which form the mitotic spindles, which separate the cells and the chromosomes. Now, we can make these microtubules up in a test tube quite simply by taking purified tubulin, mixing up in the cold with an excess of GTP, And then when we warm the solution from about 4 to 35 degrees, reactions occur. GTP is hydrolyzed to GDP, and the tubulin assembles to form microtubules. And this normally takes about 2 to 3 minutes. Now, once the microtubules have been formed, these chemical reactions continue. As I said before, tubulin is being added onto one end, other molecules of tubulin are being lost at the other, and GTP is being continuously hydrolyzed to GDP. So there's a continual dissipation of chemical energy through this system. Now, under some circumstances, what can occur is something like this, is that microtubules, if they start to grow and shrink very quickly, can leave behind them a chemical trail of liberated tubulin, and then the growing ends of neighbouring microtubules will grow into the region, preferentially grow into the region where the concentration of tubulin is the highest. And so individual microtubules can be coupled together in this way, in a manner which shows analogies to that by which ants are coupled together. Now, what you see here is the result of an experiment in which I've taken a preparation of purified tubulin and I've mixed it up in the cold with excess of GTP, and I've placed it in optical cells, which are about 4 centimeters high, with an optical path length of 1 millimeter. I've warmed the solution to 35 degrees. After 2 or 3 minutes, microtubules are formed, and then progressively, over the next 5 or 6 hours, the sort of stationary arrangement that you see here develops. And this is very unusual behaviour. It's not often one sees something like this. This is a photograph taken in reflected light, and this is a photograph taken using birefringent methods. And the fact that the preparation is strongly birefringent is telling us that the microtubules are strongly oriented in this system. And you can see this in an electron micrograph, where you can see some of the individual microtubules. Now, if we look at the disposition of the microtubules within this arrangement, we can use relatively sophisticated methods such as small-angle neutron scattering. And I shan't go into the details of this, but when we do this, we see that in individual stripes, the microtubules are almost perfectly oriented at about either 40, 45 or 135 degrees, but the difference is that the orientation is 45 in one stripe, and then it will be 135 in the next stripe. And you can see this quite clearly in this type of observation. Once again, I'm using polarization methods, but in this case, the orientations which are at 45 degrees introduce a blue interference colour, whereas the orientations at 135 introduce a yellow interference colour, and you can see that the orientation flips from left to right up the length of the tube. Now, I said earlier on that chemical self-organizing systems are comprised of variations in concentration, but what I've shown you here up to now is variations in orientation. Variations in concentration are also present, and we can show this either by, once again, by neutron small-angle scattering methods or by fluorescence methods, and the concentration drops by about 35% and then rises again every time you're in the region between where the orientation flips from left to right. And so we have both variations in concentration and variations in orientation. Now, the structure is more complicated than it appears at first view. If I look at it at closer magnification, and this is what you see here is what's going, this is one of the stripes I showed you earlier on. You can see it's comprised of another series of stripes. If I magnify that even further, there's another level of stripes. If I magnify that once again, there's another level of stripes. If, instead of making it up in an optical cell of 1 centimeter, I make it up in a test tube of 15 millimeters diameter, I see this periodicity of about 7 millimeters. And so you see, we've got a self-similar structure of stripes within stripes within stripes within stripes, encompassing several orders of magnitude. Now, this slide shows you the progressive development of the structure in a 5mm test tube. And you can see that initially, the solution is homogeneous, and the first thing that occurs is about 6 minutes, and I'll show you this corresponds to the bifurcation time in this system, where you see this vertical break in symmetry, and then a couple of hours later you see horizontal breaks in symmetry, and then after about 5 hours the structure is fully formed and remains stationary, and we can keep these structures in existence for 2 or 3 days. Now, what I've not told you is that this sort of striped arrangement always has occurred with the optical cells positioned vertically, so like this. If instead of placing them vertically, I do the experiment with the optical cell lying flat down, then I see another type of morphology, such as you see here. And this is telling us that gravity in some way intervenes in the self-organizing process. Now, before I discuss this in more detail, I'd like to point out that in these morph preparations, there's a considerable amount of positional information. And for example, if we just look at this horizontal morphology, we can see that the center of the cell is almost perfectly defined. So in some way or another, all these millions of microtubules in this preparation have worked out or calculated where the middle is, and they're manifesting it to us. Now, we can do some very simple experiments which shows that the the direction of gravity determines the morphology of the state at a critical moment early in the process. Quite simply, we made up 16 preparations, got the experiment going, started microtubule formation, and then after time 1 minute, one sample was laid down flat. After time 2 minutes, the second sample was put flat. 3 minutes, the third one up to about 20. And then we leave them lying down for the full 5 hours while the structure develops. And since they're lying down nearly all the time, you would expect them to form the flat morphology. And this is true for samples which were only upright for 2, 3, or 4 minutes. But as you see here, samples which were vertical for 6 minutes or more, only 6 minutes or more, all formed a stripe morphology identical to what would have occurred if they had been upright all the time. And so you see, the morphology that forms is determined by the orientation with respect to gravity at a critical moment, 5 or 6 minutes into the self-organizing process. Now we can do more sophisticated experiments. Some years ago we did experiments under conditions of weightlessness in sounding rockets of the European Space Agency. And in these experiments we had something like 15 minutes of weightlessness. And when you do this and expose these preparations, do experiments where the samples are exposed to weightlessness for the first 15 minutes, as you see, self-organization is very strongly inhibited. So under these particular conditions, gravity is actually triggering self-organization. Now, one of the problems we had in these space experiments is when you do them, there's a stopper at the top there which you can't see. And when you prepare the samples, if you're not careful, you can get a very small bubble of air at the top there. Now, when the payload comes back down to Earth again after 15 or 16 minutes, it's subject to quite high centrifugal forces, and the air bubble can be propelled through the preparation. This is what happened in this case, and as it's propelled through, these preparations are quite viscous. You could see a line of birefringence, and it orients the microtubules in its wake. And then, as you see here, partial self-organization has occurred perpendicular to the direction of orientation called by shearing. So this has given us a clue about the mechanism of self-organization. It's telling us that orienting the microtubules at a critical early moment can trigger self-organization. Now, another way of orienting microtubules is to use a very strong magnetic field. And what we've done in this experiment, we've not gone up into space. We've prepared the samples in the flat, lying down in the flat morphology, and this is what we get in the absence of a magnetic field, what you've already seen. And this experiment, we've applied a strong magnetic field along this direction for the first 15 minutes of the process. And as you see here, now, once again, we obtain a morphology, a stripe morphology, very similar to the vertical morphology. So we can change the morphology by applying orienting fields. Now, what you see in this slide is the kinetics for the formation of microtubules from the cold tubulin preparation. Here's the microtubule mass on this axis, same here. Here is time. Initially, the solution is cold, it's at 4 degrees C. We place it at 35 degrees C. Microtubules start to form, the microtubule mass increases, and you see this here. And after a few minutes, there's several extreme types of behavior. In this case, the microtubules form relatively slowly, and they reach a stationary monotonic value. When you see this type of microtubule assembly kinetics, then we never see any self-organization. When we see self-organization, we always see assembly kinetics of this type. The microtubules start to form quite quickly. They go faster and faster and faster. And then you see there's this overshoot. They go in so fast, they've depleted so much, they depleted the tubulin concentration in the preparation so much that they can no longer keep going. And so they start to disassemble. And when they disassemble and shrink, they once again increase the tubulin concentration in the preparation, and this progressively restabilizes their condition. And we reach later on, we reach a monotonic value. And this type of behavior, where we see a chemical instability in the relative proportions of free tubulin and microtubules, is always associated with self-organization, and it's telling us that there's an instability here. And you notice that this instability occurs around the bifurcation time. Now, what we think is going on is something like this. Initially, the microtubules form the solution, and they're growing very rapidly. The solution is isotropic, and it's homogeneous. But it gets to the point where they run out of tubulin, and they start shrinking very quickly. And when they do this, they're going to leave behind these trails of tubulin that I told you about. And now, other microtubules, which are desperately short of tubulin, because they're shrinking as well, will grow into the direction of these trails and be coupled together. Now, all it takes is some small effect which favors the growth of microtubules along one particular direction, and then the others will follow on, and self-organization will be triggered. Now, we wanted to see if this sort of hypothesis was reasonable, and so we carried out numerical simulations using the known reaction kinetics, experimentally known reaction kinetics of microtubules, and the known diffusion constant for tubulin. And we started with just 5 microtubules. Here's 2 here, and there's 3 behind. This is at different times, 5 seconds, a couple of minutes later. And you see, and here's the calculated tubulin concentration. You see these microtubules start to advance and separate themselves. They leave behind trails of tubulin, and the 3 microtubules which were behind grow into these trails. Now, instead of using 5 microtubules, if instead of using 5 microtubules, we use umpteen million of them on a reaction space which is about 100 microns by 100 microns, and we let the algorithm go, after a few hours, we end up with self-organized striped arrangements such as you see here. And if we look at the simulated assembly kinetics that correspond to this, you see we see an overshoot. And this type of behavior corresponds relatively well with experimental observation. And this encourages us to believe that this type of explanation we're proposing may not be too far from reality. Now, when we were doing these simulations, we noticed that the stripes were always along one diagonal, along the diagonal. And this led us to suspect that in some way or another we had unwittingly introduced some sort of bias, directional bias into the system. And this turned out to be the case. There was a bias in the way that diffusion was digitized and numerized. When we removed that, as you see here, although we got clumping, we don't have a striped arrangement. Well, we can now introduce a directional effect, an orientational effect. And one way is just to initially orient some of the microtubules. And this is what we'd do if we were using a method such as shearing or strong magnetic fields. And once you start to see stripes reappearing. The other way we could introduce a bias is to make tubulin diffusion asymmetric. And this would correspond to the way multi-way gravity would function on this system, in that you favorizing microtubule growth along one direction more than another. And when we do this, once again, striped arrangements develop. Now, a further aspect of these simulations is the following: is when this structure develops, I've marked here one of the bands. With time, you see it progressively advance across the reaction space at rates of a few microns a minute. Now, these microtubule preparations are extremely viscous, and here you see, so here these advancing waves correspond to waves of viscosity and concentration going across the reaction space. And this helped us to explain some other experimental behavior we had observed. All the experiments I've showed you before, up to now, the preparations were comprised simply of tubulin and GTP. What we've done now is add some colloidal polystyrene beads into the preparation. These are inert, they don't react with the microtubules in any way. They're about 1 micron in size, and what you see here are magnifications of a region which covers about one stripe. And we get the self-organizing process going, and then what we start to observe is that the beads are transported along the direction of orientation of the microtubules at rates of about 4 or 5 microns per second. And when self-organization is finished, directional transport stops. If we do the experiment under conditions of weightlessness or other conditions where there's no self-organization, then there's no transport. If we look at the distribution of beads in the preparation, after self-organization is finished, we find that they themselves have been organized into stripes. So here we see a more complex emergent phenomenon, that the system is capable of transporting particles along a given direction and themselves organizing them. Now, all the experiments I've showed you are in quite large macroscopic containers, a few centimeters high. And we were interested in biology, and biological cells are considerably smaller than this. And so we wanted to know if processes of this type could also occur in small particles. And so we made up preparations in relatively small wells of different size and geometry. Here you see what happens in a circular well. There's not a lot of organization. There's some organization in square wells. There's a lot of organization in these channels. Here you see what happens if two circular wells are joined together. Here you see the microtubule, and we immediately see the formation of a very oriented arrays of microtubules at the junction, which also correspond to regions of high concentration. And this is rather reminiscent of the disposition of microtubules during mitosis, of cells during mitosis. Now, as I've just shown you, anisotropic shapes strongly favour self-organisation, and this can be readily explained in the following way. Microtubules which are growing parallel to an impermeable boundary suffer no constraint. However, microtubules which are growing into it, obviously, they can't go through the other side, and so they stop growing or they shrink. And on average, this will favour the growth of microtubules along this axis, and this will cause a substantial orienting effect, which strongly influences, strongly encourages self-organisation. Now, this is a slightly different experiment. It's a bit more complicated. What we've done here is we've taken a geometrical arrangement in which the 5 squares are connected together at the corners. And in the first experiments, they were done in the absence of colloidal particles. And as you might imagine, we've got strong organisation at the junctions, which spreads out into the squares, and this gives rise to these concentration patterns you see here. Now, if we do it with colloidal particles present, we get a completely different type of arrangement. We find something which resembles the type of morphology we would receive for isolated squares on their own. If we look more closely at this, here you see a magnification of one of the junctions. I don't know if you can see that very well. This is a central square. There's a junction here. Here you can see the particles, and you can see here that this particle here is gradually being transported and moved towards a junction where the particles, you can see it in close up here. If you look at the junction, you see the particles are progressively accumulating at the junction where they're attenuating, preventing communication between the two between the geometrical parts of the ensemble. And so what we've got here is a quite sophisticated behaviour. You see, initially self-organisation gets going, the microtubules start to orient at the junction due to geometrical factors, forming these oriented arrays, and then the particles are transported there and positioned at this junction. And once they're positioned at the junction, they in turn modify the behaviour of the population as a whole. And so you see a type of morphology which is characteristic of isolated squares rather than connected squares. And so we've got a very simple, here we have a very simple machine because the particles are displaced in position and the system is acting as a type of valve, and the type of morphology that's being produced is an external readout of what's going on. And this is a very sophisticated behaviour for something which initially just contains 2 active components, tubulin and GTP. So I'm going to stop there. Just a few conclusions. We've got an example of a biological self-organisation by reactive processes. We have a number of emergent properties which develop: self-organisation, positional information, self-similarity, triggering by weak external factors, directional transport of organisation. It's a very, very simple system. Just tubulin and GTP, and it can do all this on its own, which after all these years, I still find quite remarkable. And it provides, what you see at the end is that you can provide a demonstration, higher order properties, perhaps eventually leading to swarm intelligence can spontaneously develop in a molecular system. So, well, I'd like to thank my co-workers, particularly Cyril Papaset, Nicola Dad, Sandra Cortez, and these other institutions that have funded us over the years. And I'd like to thank you for listening to me.